Hi, my name is Frank Verlet and I work at the Department of Health Sciences at VU University. In this video, I'd like to explain how we can describe our data when actually our observations in our populations are clustered. And the reason for doing that is the method of describing this data is often used in several statistical models. But let us take us one step back. So in this corner, I have created a small graph that indicates here on the x-axis a continuous variable with all kinds of observations. And all observations together form a distribution. And you can see that each observation is part of that overall distribution. The most simple way to summarize a distribution is actually to take its mean value. So we can draw a line and we could say the mean value of that x factor is the mean value of x. But we can only do that if each of these observations is actually independent, which means that one observation has no influence on the magnitude of the other observations. But you would be surprised how often this assumption of independence is not true in our data. We say that our data are clustered. And a classical example is when we want to assess school performance in students, because these are very typical clustered data. And why is that? Because students are part of certain schools. So we can say we have different schools, but in each school we also have different classes. And within each class there are of course different pupils. Now, two pupils from the same class are much more alike in their performance than two pupils from different classes. And why is that? Because pupils from the same class share some common characteristics. For instance, they all have the same teacher, and the type of teacher might influence their performance. If we look at health sciences, we often look at the occurrence of disease in a population. And also here we very often have clustered data, because we know that our participants are, for example, geographically clustered. We can have a province, and within each province we have districts, and within each of these districts we find our participants. Typically clustered data. So now if we go back to our original distribution, we actually have to admit that this is clustered data when we can identify multiple groups in that population, like I indicate here. So if we stick with the health science example, these might all be different districts. And the information from all these districts make up our total population, our health outcome. So let us now take one of these districts separately. So we move that district over here and we draw it afresh. So we have an x variable and we can see that that x variable have different observations and that observations form an overall distribution. Now within the district, all these observations are independent. We see that there are no further clustering within the districts. So now we can do what we wanted to do in the beginning, to summarize this distribution by its mean value. But there's something else we can do. Each and every observation is part of the distribution. like here. And I quickly draw all those dots. So apart from just the mean value, we can also calculate how far an individual value is removed from that mean value. Sometimes it is far removed, and sometimes, like here, it is actually very close to our mean value. And we call this distance, we call it the error, indicated by an epsilon. And we use a iota here to indicate that it is the error of an individual observation. But as we have seen here, there are multiple districts. So we can actually extend this graph and just assume that we have a second district. And of course, we can just then copy the whole procedure, what we have been doing in the first district. We have all these observations being part of the distribution. We calculate the mean value of that district, and for each observation we identify the individual error. But as we have discussed here, there's even another layer of clustering in our health data. That is the province. So these two districts are actually part of the same province. And it would not be surprised that we then can summarize the different districts into a single province. Because now the distribution of this province is made up of all the different mean values of all those different districts that are part of that province. So we have an observation here, and we have an observation here, and we can take again the mean value of the province. And just like we did with the individual values, we can calculate how far the mean value of one district is removed from the mean of the province, and here from the other district. So we use mean values of the cluster components to describe our data. So in this graph, I have now summarized the information that we had in the earlier part of the video. So what we can see here in pink is our total population, where we started with. Here in blue, we have the information of the first level of clustering, the districts. And in green, we have the second layer of clustering, the provinces. Because we should not forget that we had province that had different districts, and each district had participants. So the first level of our data is participant. The second layer of our data is district. And the third layer of our data clustering is the province. The reason why I summarize it is because we're going to talk about some statistical notation. We need to have ways to identify all the components of our clustering. So we start by labeling our individual observations of the participant as level I. So participants is level I. The district we call level J. And the province we call level K. And let me change quickly the color. Oh no, that's not going to work. No, sorry. Let's so we have three levels of data: I, individual; J, district; and K, the province. Together, they make up the total population. So what we have discussed before is that the individual observations within a district are independent of each other. There is no level of clustering anymore. So we can summarize each district with its mean value, which we do here and this district. And the faraway district, we also summarize it with the mean value. And within each district, we were able to identify the distance that an individual observation is removed from that district mean. So we have an observation here, we have an observation here, and of course that also happens in the other districts. And we have discussed earlier that we call this epsilon iota, epsilon I. We've also seen that within the province, each district mean is independent from each other because there is no level of clustering anymore between province and district. So we can also then summarize our province by the mean value of all those district means. And we can also do that in the second province. And just like within the districts, those mean values are now independent, very independent observations, so we can use the distance between the individual observation and the province mean. And we can also do that, of course, in the other district. So now we have all three levels of clustering summarized using all the data available. And by doing that, we are able to describe each and every individual observation. So let us focus on this far of observation, this observation. This observation, the value of that, so the value, the outcome variable, we always call that y, can be described as follows. First of all, we have a distance between the individual observation and the district mean, the district to which that individual belongs to. We also have a distance where the district mean is removed from the province mean. And we have how far the province mean is actually removed from the total mean. We did not draw that, so I will draw that now. We have the distance here, and this province mean is removed so far from the total mean. So we now have identified three components within our population, and we can use these components to actually describe an individual observations. So let us start from this side. So this is the distance that the province mean is away from the total mean. And let us call that mu k, and that k refers to this k of the province. Then we have a component that identifies how much a certain district within that province is away from the province mean. We also call that mu, but now we call it j to identify the J of the province, sorry, of the district and the district here. But because we have multiple provinces, we also need to identify that this district is part of a certain province. Yeah? So this is a single province, and this is a district within a certain province. And within the districts, we have the epsilon, the individual difference between the individual observations and the district means. That is from the individual in a certain district in a certain province. So this observation can be described as the observation of individual I in district J in province K. We can describe it as the mean value. We call this now mu, plus this distance, mu k, plus this distance, mu j k, plus the individual error, so that is the error of individual j in district j and cluster k. So here we show that how we can describe our data in the situations where our data are clustered. So we used information of each of the clusters and combine that information in a single formula. And why is that important? Because, like I said in the beginning, this is a concept that is used in very many statistical models where there is no independence. And I will explain that in another video when we talk about mixed effect models. So I hope this video was of your interest and that you get now a good grip of summarizing your data in the situation with clustered observations.